Hi, welcome to the third session of Computer Organization and Architecture. Today we will be discussing about machine instructions and programs. Before learning the machine instructions and program, we need to understand how to represent the input which is given to the computer system. All the computers deal with numbers and characters. We should understand how to represent the numbers as well as the characters. So now if you consider the machine instructions, while writing the instructions, while giving the input, we will be representing the numbers in the form of 0 or 1, because the computer can understand only the two values, two level electrical signals, that is 0 and 1. And we call that 0 and 1 as bit of information, where bit stands for binary digits, and the amount of information represented by a bit or 0 or 1 is called as bit of information. And while giving input, we are going to represent a string of binary numbers, string of zeros and ones. So that is how we give the input to the computer system. And while giving input, that is 0 or 1 or binary digits, we have different number systems to represent the inputs. And the three such systems are, that is, in number representation, we have three systems. The first one is Sine and Magnitude. Sine and Magnitude. The second one is ones complement. And the third one is twos complement number system. So these are the three number systems. There are several number systems. Under that we are going to discuss three number systems. And before discussing this, let us first see how to represent a binary string in general. If you consider a binary string, let us assume B is the binary string. So it will be represented as Bn minus 1, Bn minus 2, etc. B1, B0, where Bi can be 0 or 1, and this value ranges from 0 to n minus 1. If you want to represent this in the form of an integer, then the integer equivalent, unsigned integer equivalent of this binary number is V of B, which is represented as Bn minus 1 into 2 to the power n minus 1 plus Bn minus 2 into 2 to the power n minus 2 plus etc. plus B1 into 2 to the power 1 plus B0 into 2 to the power 0. So this is how we represent the unsigned integer equivalent of the binary representation what we have written. So this is the general representation, and these are the three number systems using which we can represent the binary strings. So now let us consider a table wherein we will be observing or seeing the representation of 4-bit binary string in all these different number systems, so that we can understand the difference between these number systems. Yes, let us consider the table. Binary Sine number representation. So if we consider 4-bit numbers, you will be having 16 combinations. So let us represent the first column as B. So the bits are B3, B2, B1, B0. And let us consider all the three systems. The first system is Sine and Magnitude. Second system is ones complement. And the last system is twos complement. Okay, let me represent all the 16 values, and then I'll tell you what is the difference from one system to the other system. Yes, so instead of starting from 0, 0, 0, I'll be starting with 0, 1, 1. So there is The significance I'll tell you later. 0 1 1, okay, then 0 1 1 0, 0 1 0 1, okay, I'll continue the same table here. So there we have 8 values, another 8 values I'll be writing here. So first column is binary string, next is sine and magnitude system representation, and one's complement form of the binary string. The last we have 2's complement form of the binary string. Yes. So now let me complete the another 8 values here. So this is the representation of binary strings. Yes, now let us consider the first system, that is sine and magnitude. So here the first thing you need to understand is the MSB bit is used to represent the sign. If you have 0 in the MSB, that represents positive number, and 1 in MSB represents negative number. This is common in all the 3 number systems. So if you consider the first number system, that is sine and magnitude, the representation is very simple. So if we have 0, it is a positive number. So since we have all zeros here, so the sign for all the numbers is plus, all are positive numbers, and we are going to consider the equivalent of the rest of the 3 bits in order to represent the magnitude. Yes, we have 1 1 1, that represents 7. So how it is equal to 7? So I have already given you the integer representation v of b. So according to the v of b, if you consider this 1 1 1, okay, yes, we have binary bits as 1 1, okay, 1, and if you consider the weights of the powers of 2, okay, so into 2 into 2 into 2, so the first lowest power is 0, next 1, next is 2, 3 we are not going to consider. Why? Because this I have already told you, this is the representing, okay, the MSB is representing the sign of the number. Therefore 0 is used for representing positive sign, and the rest is used for representing the magnitude of the number. Yes, 1 1 1, it is equivalent to 7. If you convert, okay, this is 4, 1 into 4 plus 1 into 2 plus 1 into 2 power 0 is 1 into 1. So it is equivalent to 7. So similarly we are going to consider the magnitude of all the other numbers. So if we consider this string, this is equivalent to plus 6, plus 5, 4, 3, 2, 1 and 0. So now coming to the negative number representation. So since we have 1, okay, in the MSB, we are going to consider the sign of all these numbers in sine and magnitude system as minus, okay, and the magnitude equivalent of rest 3 bit will be found out as usual as we discussed earlier. So we have 0 0 0, it is equivalent to 0, 0 0 1, 1, 2, 3, 4, 5, 6, 7. So this is the representation of binary string in sine and magnitude system. Coming to the 1's complement and 2's complement, let me consider first the 1's complement. So 1's complement is nothing but taking the complement of given string, complement in the sense negating the bits. Yes, so now let us consider 1's complement, and one thing here we need to understand is the positive number representation is same for all the 3 systems. So if you consider the MSB, which is 0, all these are positive numbers. Therefore even in 1's complement there is no change in the magnitude of these numbers and sign of these numbers. So all are positive numbers and magnitude remains same, that is 7, 6, 5, 4, 3, 2, 1 and 0. So even in 1's complement form the positive numbers are represented as it is, and if you come to the consider the 2's complement form, here also the positive numbers representation will be same, there is no change. So all the numbers are same as sine and magnitude and 1's complement number. Yes. Now coming to the negative number representation, here we can see the change in representation of the numbers. If we consider 1's complement form, here we have a string 1 0 0 0. So here we have the sign bit. So the sign of the number is minus. Since we have 1's complement representation, we need to take the negation of these bits. Negation of these bits is nothing but 1 1 1. Therefore this is equivalent to 7. The sign is minus and the equivalent magnitude equivalent for this string is minus 7. Okay. And similarly, if we consider the next string we have 1 0 0 1. Okay. Here this represents the sign, that is negative, whereas we have 0 0 1. So if you consider the 1's complement, that becomes 1 1 0. Therefore 1 1 0 is nothing but 6. So this represents minus 6. Similarly, so we have minus 5, minus 4, minus 2, minus 1, yes, minus 3, minus 2, minus 1 and minus 0. Okay. So this is the representation in 1's complement. And if we consider 2's complement form, while taking 2's complement of a number, so first what we do, we take the 1's complement. Let us consider as an example. Okay. 1 0 0 0. If we consider 2's complement is nothing but taking 1's complement and adding 1 to the 1's complement. This results in 2's complement of a number. Now let us see, so what are the equivalent for these strings in 2's complement form. Since MSB is 1 for all this, so we have minus sign for all the numbers. And coming to the magnitude, yes, let me consider 1 0 0 0. So out of this, so let me remove the 1, so which is the sign bit. And now if you consider 2's complement is nothing but 1's complement plus 1. 1's complement of 0 0 0 is 1 1 1. So plus 1 we need to add so that it becomes 2's complement. So when we add 1, so 1 plus 1 is 0. Okay, and carry is 1. And once again 1 plus 1 is 0, carry 1, 1 plus 1 is 0, 1. So if you find out what is the equivalent of this becomes 8. Therefore we have minus 8 as the equivalent for 1 0 0 0. Similarly, if you find the equivalent for the rest of the binary strings, we have 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, and lastly we have minus, okay, sorry, this is the last bit, so minus 1. Okay, yes, so this is the 2's complement form of representation. And if you observe, so there is change in the negative number representation. And one more important point to note here is we have plus 0 and minus 0 in sign and magnitude and 1's complement form. But whereas in 2's complement we have only plus 0, instead of minus 0 we have minus 8 in 2's complement form. Now if you consider computer system, so we are going to make use of 2's complement number system so that we can represent or we can perform arithmetic operations easily. Why? Because if you consider sign and magnitude and 1's complement system, these systems result in incorrect result when we perform arithmetic operations. So that can be seen by considering any example here. If you consider sign and magnitude and 1's complement form, this will result in incorrect result. Because of that reason, we are going to make use of 2's complement form in order to perform addition, subtraction and any other arithmetic operations in a computer system. Okay. Yes. Now, after understanding the number representation, and which is the most commonly used number system, we have to learn basic arithmetic operations in computer system so that we can understand how the computer manipulates the given data. Not only while performing the arithmetic operations, even while calculating some memory locations, the computers perform arithmetic operations on the numbers or the memory addresses what we have So because of that reason, in order to understand how it is going to manipulate the data, we need to understand the basic operations, arithmetic operations that is performed on the given data. Arithmetic operations. So let us consider addition of positive numbers first. Addition of positive numbers. Yes, in order to understand addition of positive numbers, so let me consider addition of 1-bit numbers first. So what are the possible combinations we can have when we consider 1-bit number? Since we have addition, we will be having two operations, two operands. So you will be having 4 combinations. The combinations are 0, 0, 0, 1, 1, 0 and 1, 1. So these are the possible combinations we can have. 0, 0. When we add these 2 bits, the result is 0. 0, 1, 1, 1, 0, 1, 1, 1. When we add, the result is 1, 0. Okay. Here the 0 what we have is sum bit, and this is called as carry out in addition. Okay. So this is the addition of 2 bits. That is 1 bit, addition of 1 bit having 2 operands. Okay. Now if you consider addition of multiple bits, it is done as usual as we consider the manual addition operation. In the similar way, the addition is performed. Say for example, if you consider 2 bits for one operand, then let me consider, so the combinations as 1 0 1 0 and 1 1 1 1 0 0 1 1 as an example. So addition of this, 0 plus 0 is 0, 1 plus 1 is 1 0. Okay, that is 0, carry is 1. So out of this, these 2 bits represents sum and the carry out bit is 1 in this case. And if you consider addition of 1 1 1 1, so 1 plus 1 is 0. We have 1 plus 1 plus 1, this results in 1 1. Here the sum is 1 0 and this is carry out. And here 0 plus 1 is 1, 0 plus 1 is 1. So this is sum. So this is how the addition of positive numbers is done. But when we consider positive addition of sine numbers, so it will be a different case that we will be discussing next. Yes, so now let us consider addition and subtraction, the basic operations, arithmetic operations, that is addition and subtraction of sine numbers next. Yes, addition and subtraction of sine numbers. We have already seen 3 number systems, and I have already told out of 3, 2's complement system is the one which we are going to use in order to perform any arithmetic operation in a computer system. If you consider sine and magnitude, it is very simple. It is similar to the integer addition and subtraction what we perform. But if you consider in a computer system, it will result in incorrect result. Because of that reason, we are going to use 2's complement for addition and subtraction. In order to understand the addition and subtraction of 2's complement numbers, we consider modulo n, addition or subtraction, which is represented as mod n. Yes. So in order to understand mod n addition or subtraction, so we have a graphical device. Even without that also we can do, but we have a graphical device using which we can easily understand the addition and subtraction of 2 numbers. So let me consider the graphical device so that we can understand how the addition and subtraction is performed in 2's complement form. Yes, so the graphical device consists of n values 0 through n minus 1. So starting from 0, we will be having 1, 2, etc. minus 1 n. Okay, so these are the different values you will be having. And now in order to understand, as an example we will consider mod 16 number. So this is general representation of a circle with 0 to n minus 1 values. So this is a modern representation. And now we will consider mod 16 addition and subtraction, and for that we will consider mod 16 circle having 16 values 0 through 15. Yes, so 0, instead of writing integer 0, I will consider binary string 0 0 0 0. Okay, next is 0 0 0 1. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and lastly we have 15. Yes, let me represent the 2's complement numbers inside, that is 0, this is plus 1, 2, 3, 4, 5, 6, 7. So this is minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2. Yes. Okay, yes. So this is the graphical device we have. So now let us consider as an example the addition of 5 plus 4. If you consider 5 plus 4 mod 16 addition, so 5 plus 4 is equal to 9. So now we are supposed to find out how to use this graphical device in order to find out the sum of 5 plus 4 as 9. So initially we are going to locate 5 on the graphical device. Where do we have 5? So we have 5 here, and we are going to rotate this circle clockwise 4 times. So the second operand we have is 4. So we are going to rotate this circle 4 times clockwise in the clockwise direction, so that we can result in 9. So here we have 5. Once we rotate, okay, we get 6 as the next number. Second time when we rotate, 7, next A, this is okay, minus 8, but do not consider this, okay. Instead of that, we will consider the number which is written outside. So in order to find out the addition of the positive numbers, okay, let me consider. Then we will, if you consider the negative number, we will consider the whatever the numbers what we have written inside. So now since we have addition of positive numbers, so let me consider the positive numbers which are written outside, or binary strings which are written outside. 5 plus 4 is 9. So 5, here we have 5. Once we rotate, we get 6. Second time 7. Third time 8. Fourth time 9. So we get the result as 1 0 0 1. Okay. So this is the addition of 5 plus 4 in mod 16 number system. If we consider subtraction using this circle, mod 16 circle, so let me consider as an example 7 minus 4. 7 minus 4 results in plus 3. So here what we are going to do is, we are going to consider 7, the representation of 7. So this is 0, 1 1 1. For minus 4, so the representation is 1 1 0 0. Yes. So in this case, we are going to locate 7 on the circle, and we are going to move 12 times the circle in the clockwise direction. So in the, by subtracting, we are going to consider 2's complement form of minus 4, and its equivalent will be found out, and we are going to rotate the circle So 12 times in this case in order to get the result as plus 3. So now after understanding the addition and subtraction, if you want you can consider few more examples of addition and subtraction. And if you consider plus 2 plus 3, so addition of two numbers, that is positive numbers. Yes, what is the equivalent for plus 2? Plus 2 is 0 0 1 0, plus 3 is 0 0 1 1, and addition is 1 plus 0 is 1 0 1 0. If you observe, so we have 5 plus 5 as the result. So in this case, locate 2 on the circle, rotate the circle clockwise 3 times, so in order to get 5 as the result. Similarly, if we consider addition of minus 2 and minus 7, okay, or let me consider minus 2 and minus 4, okay. So addition of this is minus 6, minus 2 and minus 4. So in this case, 2's complement of minus 2 is, yes, minus 2 is 1 1 0 1. 1 1 0 1 is 2's complement of minus 2, and 2's complement of minus 4 is 1 1 0 0. So locate this equivalent of this is 1 1 0 1 is 12 plus 1 13, and this is 12. So locate 13. So 13 is here. So rotate the circle in the clockwise direction by 12, that is 12 times, so that you get the result as minus 6. So that is how we make use of this graphical device in order to find out the result of addition and subtraction. Okay. Now if you consider the two operations, addition and subtraction, the general rules are, if you consider addition of a positive number of positive numbers, the result will be a positive, and this result is, or the sum is correct until unless it is within the range. If it is within the range, then the number is correct or output is correct, and if it is if we have any carry out, okay, in this case we do not have any carry out. If we have any carry out, we are going to neglect it and we are going to consider, so these bits as the result of addition. If we consider subtraction, so here also we are going to perform the same operation as addition. If you observe, so here also we are going to locate the first operand on the circle, and we are going to rotate the circle clockwise direction as number of times as the second operand. Here also we are going to do the same. So in 2's complement form, so that is the advantage we have. For both addition as well as subtraction, we are going to perform the addition itself, same operation itself. Okay. Yes. So in both the cases, the output should be within the range. So that is, the range is 2 to the power n minus 1 to 0. So this is the number representable form. So we have to see that the output or the result is within the range. So this is addition and subtraction operation. And now if you consider addition and subtraction, so we can observe in some cases there will be an overflow. So overflow is nothing but, as we just discussed, so the sum is correct or difference is correct only when the result is within the range. So if you consider any result that is out of the range, then we say there is an arithmetic overflow. So next topic is overflow in arithmetic operation. Overflow in arithmetic operation. If you consider overflow, so if you consider addition of two positive numbers, as we discussed earlier, if you consider 9 plus 7, so we get the result as 16. This is integer addition. So if we consider the binary equivalent, so 9 is 1 0 0 1, 7 is 0 1 1. In this case, so we have 0, okay, this is the binary equivalent of 16. If we consider, so we have 0 0 0 as the sum bit and this as the carry out. Since this do not fall within the representable form, that is within the range, we can represent only 1 1 1 1 as the highest number when we consider 4 bit. So since we have 1 0 0 0 0, in this case we say an overflow has occurred. But if we consider the addition of negative numbers, so this is not the case. By simply verifying whether we have C out or not, we cannot say the overflow has occurred or not. So in order to check whether the overflow has occurred or not in case of addition of two negative numbers, so we need to consider an example in order to understand how to check the overflow or what we can conclude when the overflow can occur. So whether only in case of we have a C out or do we have any other cases. So in order to understand that, let me consider a example. Okay, yes. So now in order to understand when the overflow can occur in sine number system, okay, let me consider an example of adding 7 plus 4. So both are having same sign. When we add 7 plus 4, we get the result as 11. So now 0, 111 is the representation of 7 and plus 4 is 0, 100. Okay, yes. So 1, 1, 0, 1. So 8 plus 3 is 11. So this is the equivalent of 11 in binary system. If we consider the addition of 7 plus 4, the result is 11. Even though we say it is within the range, but when we consider the sine number system, so that is whatever the representation we have inside. So this is actually equivalent to, see, 1011. Where do we have 1011? We have 1011 here. So in 2's complement form, this is equivalent to minus 5. So even though we do not have any carry out, we have an incorrect result when we consider sine numbers. So if we consider similarly, okay, if we consider addition of minus 6 and minus 4, in this case, so you get the result that is equivalent to 1010. So which is equal to minus 6, once again, which is an incorrect result. Therefore, if you consider overflow in case of arithmetic operations in 2's complement form in sine number system, then you cannot conclude only by inspecting the carry out from the MSB to check whether there is a overflow or not. In order to conclude when we can have overflow, we can verify these two numbers. So if you verify, so we have positive sign for both the inputs. In this case also we have negative sign for both the numbers. Therefore, we can conclude that overflow can occur in two cases. The first case is whenever there is an C out from MSB, whenever there is an C out from the MSB, and second case is when we have same sign for the two operands. So these are the two cases when we can expect the overflow in case of arithmetic operation when we consider sine numbers. Next, after understanding the number representation, so in this class we will be learning how to represent the characters. So as we discussed in the beginning itself, so we usually give the input as either number or characters. Now we learned the basic operations that can be performed on numbers. Now we will be discussing how to represent the characters. So characters can also be represented by using the binary strings, and those are called as character codes. So characters can also be represented using binary string. So those are called as character codes, and usually when we press a key, so that will be converted into ASCII values, 8-bit ASCII values. So that gives you the equivalent of binary for a given character. Thank you. So we will be discussing the next topic in the next session.